Warning: the following video contains engineering concepts that involve a lot of algebra. Viewer discretion is advised. Yo, what's up guys, it's Hoki, and today I'm not playing Halo. Hell, I'm not playing any video games at all. So, I hear that a lot of you have been asking me for the next episode of Hoki School of Halo 2, so as a response to that, I want to show you what I've been up to since I stopped making videos so that you'll get some idea of why I haven't had time to focus on YouTube at all. So, as some of you may know, I'm currently a senior in college studying civil engineering, and while there are a ton of different areas of civil engineering, my main focus is on structures. So today, I'm going to show you how to design a very basic structure, like this one. This lovely little number here is a simple framing plan for a very generic 900 square foot apartment, and today I'm going to show you how you would design the beams and girders for it. Now, yes, I know. Normally an engineer could do this in like 10 seconds using a computer, but it's, the classic, you need to know what you're doing in order to properly use the software, garbage in, garbage out. So today you're going to get a crash course in structural analysis and structural steel design. These are pretty advanced topics for anyone outside of civil engineering, though if there are any licensed civil engineers watching this, I do recognize that I'm just a student, I'm not an expert, and this is a really basic and oversimplified example compared to what you'd see on an actual structure. But for the rest of you, I really don't have time to explain all the necessary background information and prerequisites, or else this video would be like 4 hours long. So for most of you, you're just going to have to press your I believe button and try to absorb as much of it as you can. Hopefully I can make this interesting enough to spark an interest in civil engineering in at least one or two of you. So this structure is a 30 by 30 foot square with columns at the four corners, two girders running in the north-south direction which frame into the strong axis of the columns, and six beams running in the east-west direction. Actually, these two members are technically girders since a girder is defined as a member that frames directly into a column, but semantics. They're still going to be the same size as the other four beams. Okay, so first thing we have to do is calculate our loads. Now, for this type of structure, we would only consider two types of loads: dead loads and live loads. Dead loads are basically the weight of the building materials themselves, such as the metal deck and the concrete slab, and are defined as loads that do not or cannot move. Live loads are loads that move or that can be moved, things like furniture, people, vehicles, and heavy machinery. Well, for our dead load, we would check the manufacturer's literature for the weight of the metal decking we're planning on using and the thickness of the concrete slab, but since this is a fictitious example, we'll just use 50 pounds per square foot, or PSF, which is fairly realistic even though it's completely made up. We also need to account for the weight of the non-load-bearing partition walls that are going to shape this apartment, so we add an additional 10 PSF to our 50 PSF to get a total dead load of 60 PSF. As for our live load, we look at table 4.1 in the ASCE 7 for the live load rating for the floor beams of a private residence, and we find it to be 40 PSF. From that, we want to calculate our factored loads, which is going to be 1.2 times the dead load and 1.6 times the live load. Again, the numbers to use for these load factors are found in the ASCE 7, so that's going to come out to be 72 PSF for the factored dead load and 64 PSF for the factored live load. For the combined loads, we just add things up. We get 100 PSF for the combined unfactored load and 136 PSF for the combined factored load. These values are going to be useful to have on hand, so I'm just going to keep them over here, and I'm just using a prime symbol to indicate the factored loads. Now we need to find the tributary width of our beams, which is defined as half of the distance from one beam to the next closest beam on both sides of the beam. Mathematically, this is also the same thing as the average of the two distances. So when the beams are evenly spaced, the tributary width is simply the same as the distance between the beams, which in this case would be 30 feet divided by 5 spaces, which equals 6 feet. If we multiply our loads by our tributary width, we get a uniform distributed load on each beam. We generally want our uniform distributed load to be in kips per foot though, and a kip is short for kilopound, or 1,000 pounds, so we just divide by 1,000 to convert from pounds per foot to kips per foot. So now we have the free body diagram for one of our beams, and we assume that the other 5 beams are simply identical. Here's our beam with a uniformly distributed load W and a length L. L is going to be a constant value of 30 feet or 360 inches, but I'm leaving W as a variable because it's going to vary depending on if we want to use factored loads, unfactored loads, or just live load. The next thing we need to do is determine the maximum shear and maximum moment on this beam. What's shear and moment, you ask? Well, they're types of forces that occur in the beam, and they're important to understand because they determine if and how the beam might break. For example, moment is basically a measure of how much something can bend before it breaks, like my ruler here. Shear is a little trickier to explain, and really the best I can do is with a picture. Basically, it's how much force is placed on the beam, or in this case the bolt, in opposite directions that causes pieces of the material to try to slip past each other and break. A good example of shear in action is with a bolt cutter. There are no actual blades on this cutter, but squeezing the handles places more shear on the bolt that it can withstand, and it breaks, which is what we wanted. For our example though, in order to pick a strong enough beam for our framing plan, we have to know just how much shear and moment is going to be placed on said beam. And lucky for us, there are formulas in our handy dandy steel manual that we can use. This diagram shows that a simply supported beam with a uniform load on it will have a maximum shear of WL over 2 and a maximum moment of WL squared over 8. Understanding where these formulas come from requires an understanding of statics and mechanics of materials, which I'm not going to get into because it would take another 10 minutes to run through it and would probably bore most of you to tears. So anyway, for shear and moment, we use W associated with our combined factored load, which in this case is 0.816 kips per foot. And then we plug in 30 feet for L, and we get a maximum shear of 12.24 kips and a maximum moment of 91.8 kip feet. Now that we know our maximum shear and maximum moment in the beam, we can properly design it. Doing so requires that we satisfy 4 design equations: moment, shear, combined load deflection, and live load deflection. First equation we're going to look at is moment. To put this equation into words, it says that the required plastic section modulus Zx of the beam must be greater than or equal to the maximum moment mu divided by the strength reduction factor phi and the yield strength Fy of the material. This equation might seem a little intimidating at first, but we actually know all 3 of the values on the right-hand side. Mu is our maximum moment, which we just found to be 91.8 kip feet. The strength reduction factor is going to be 0.9 for flexural bending, and the yield strength of the material is going to be 50 kips per square inch, or KSI, assuming we're using A992 grade steel, which is what you're supposed to use for structural steel members. Now, we have to be careful with our units, however, because we have moment in kip feet, but yield strength in kips per square inch. We need to multiply by 12 to get our moment into kip inches. We do that, and we get that the required plastic section modulus of our beam must be at least 24.48 cubic inches. So with this information, we can refer to our handy-dandy steel construction manual, which has a table of different sizes of I-beams, more formally referred to as W shapes, sorted by their Zx value. Concerning beam selection, we want to select the lightest possible beam that is sufficient enough to carry our load because the cost of a beam is predominantly determined by its weight. Conveniently enough, the second number of a W shape is how much that beam weighs per foot, so we can use that number to select the lightest allowable section. These bold numbers indicate the lightest beam in a group as the Zx value progressively increases. For our problem, we need a beam with a Zx value of at least 24.48. This W12 by 19 seems to fit the bill, so we'll start off with that. Now we take that beam and test it to see if it can withstand the shear being placed on it by our load using our second design equation. This equation is actually completely unnecessary because the right-hand side value is given right here in the steel manual, with the appropriate value of phi taken into account. If perchance you wanted to calculate this yourself, you could do so by referring to this table in the steel manual. You can see the depth D shown here in the diagram and the web thickness TW shown here, which then have their values listed here and here. The strength reduction factor would actually be 1.0 unless you have a slender section, which is noted right here with the little V symbol, and the footnote at the bottom of the page even tells you to use 0.9 instead of 1.0. VU, of course, is our maximum shear of 12.24 kips that we already found. 12.24 kips is less than the 86 kips that the beam can withstand, so our beam passes the shear test. In my admittedly limited experience, beams longer than about 5 feet almost always pass the shear test, and by a huge margin as well. Next is our test for deflection. Deflection is definitely the easiest design concept to understand, even if it's one of the hardest to calculate. Deflection is how much the beam moves downwards when a load is put on it. We're going to be comparing this deflection against the deflection limits outlined in the International Building Code, or IBC, which states that for floor beams, the maximum allowable deflection under the combined unfactored dead and live loads is L over 240. So that's how we get delta is less than or equal to L over 240. Delta is the maximum deflection of the beam in inches. Again, this example of a uniform distributed load on a simply supported beam is so simple and so common that this formula is not going to be difficult to find, and it's going to be 5WL to the fourth over 384EI. Now, let's confirm what we know about each of these variables. We have L, which is the length of our beam, which we need to express in inches. W is our combined unfactored uniform distributed load on the beam, and we have to express it in kips per inch so that our units work out. E is the modulus of elasticity, which is generally accepted to be about 29,000 KSI for steel. And finally, I is the moment of inertia about the strong axis of the beam, which we get from the steel manual. For this W12 by 19 section, IX is going to be 130 inches to the fourth. We plug all that in, and it boils down to a deflection of 2.9 inches, which is greater than our maximum allowable deflection of 1.5 inches. And this is no good. It means that our chosen beam wouldn't necessarily break, but it would deflect too much, and that means it could possibly cause other structural or non-structural damage to our building. So we need to pick a stronger one. Through the magic of algebra, we can find that IX must be greater than or equal to 251 inches to the fourth, so we head back to our steel manual and select a new beam. This W16 by 26 seems to fit the bill, with an IX of 301 inches to the fourth. And since it's a stronger beam than the other one, we don't have to go back and recheck shear and moment, since we already know it'll pass them. We plug in the new values, do some algebra, and hey, what do you know? The new beam works because it only deflects 1.25 inches, which is less than the maximum allowable 1.5 inches. Now we run one more check, which is to use the value of W associated with just our unfactored live load, which is 0.240 kips per foot. But this time we compare it to a maximum allowable deflection of L over 360 instead of L over 240. We plug all that in, convert our units appropriately, and we get 0.50 inches, which is less than the maximum allowable inch, so it passes the live load deflection check. And this means that it passes everything, so it's going to be the size of beams that we use for our floor beams. We have successfully sized the floor beams for this apartment. Yay! Now, designing the girders is mostly the same process. The main change here is to the free body diagram. Instead of a uniform distributed load, you have 4 equally spaced point loads, and you only have 4, not 6, because these two members frame directly into the column and they don't affect the size of the girder. Now fortunately, you can still find formulas for maximum shear, moment, and deflection in the steel manual without having to derive them. You just have to figure out a value to use for P. I'm not going to go into it, but it would be based on the value of the support reactions from the beams. Once you know all that, it's just the same process with the 4 design equations in the steel manual. Now, as I stated at the beginning of the video, this problem is really very simple compared to what you might see in an actual structure. For example, your beam could have overhanging ends, or instead of being simply supported, it could have a fixed connection, or it could be a continuous beam with more than just 2 supports, which is what we call an indeterminate structure. Not to mention that the column layout could be a lot more complicated than a simple 30 by 30 foot square. I want to emphasize that this video isn't trying to say, look at me, I'm a super expert in steel design. No, it's just what I've learned about steel design so far. I haven't even come close to learning everything there is to know about steel design, and I probably never will. And there's going to be so much more to continue learning even after I graduate. So, congratulations and thank you to any of you who made it this far without clicking away. I really appreciate you watching the entire thing, and I hope you learned something about engineering from it. As you can see, I've been kind of busy, because the problem I did for this video is pretty similar to something that I actually did for my senior design project, with a few numbers changed here and there. And this video doesn't even begin to get into the design of the columns, which we had to do, let alone things like wind load, snow load, seismic loading, and lateral bracing. And even then, my senior design project is just one class out of 5 that I'm taking, not to mention my efforts to prepare for the Fundamentals of Engineering exam. Anyway guys, that's going to be it for this video. I hope you enjoyed it, I hope you learned something, and I hope that you'll be patient with me concerning the release of the next episode of Hokie School of Halo 2, which I'm not going to start working on at all until I graduate in June. Until next time, I'm Hokie Bird, and I'm out. See you later, guys.